right, so we've been recently covering different ways to make our models kind of be able to handle more covariates or more predictors via this shrinkage, which can really provide a lot of power for our analyses. And for that, we've been talking about applying these shrinkage methods particularly to linear models. But one thing, so when we talk about linear models, the actual relationship between the individual x's and the y, the outcomes, the individual predictors and the outcome, they need not be linear. You can, of course, include transformations of those variables to account for nonlinearity. And so that's what we're going to be talking about today, basically using the same kind of linear model framework that we've been talking about so far, but how to build in the flexibility of nonlinear models. And so what have we used so far to deal with nonlinear relationships? If you remember back, I believe it was lab 2, you did this, I think we were looking at the horsepower variable. We used polynomials. And so a polynomial is basically when you include kind of higher order terms in your model. So in this case here, I've got an x variable, so a single predictor, and I'm seeing its relationship with y. But instead of just looking at the kind of, if I just looked at this first part of the model with all of these beta coefficients being 0 and the subsequent parts, we would just be looking at the linear relationship between x and y. But because I'm adding in these higher order polynomials, I'm able to look at a more flexible relationship. And so we can look at polynomials, like x squared, x to the third, x cubed, all the way up to x to the d power. And so that's what this picture is basically showing, that as we're increasing the polynomial or the degree of polynomial that we're looking at, we're fitting a more and more flexible model. And of course, that's what you saw in that lab where you were doing cross-validation and picking the polynomial degree that was appropriate for looking at the relationship between horsepower and miles per gallon. So this data that I'm plotting here, this is from the Columbia World Fertility Survey 1975 to 76, and it's examining household composition. And so on the x-axis here, I have age, and on the y-axis, population. And so what I fit here is a fourth degree polynomial. And so I fit a polynomial that looks at y here is the population, and x is age. And so this model would be population equals beta 0 plus beta 1 age, plus beta 2 age squared, plus beta 3 age cubed, plus beta 4 age to the fourth, plus epsilon. This is a fourth degree polynomial. So how is it done? Well, in practice, what happens is new variables are created, and it's treated the same as multiple linear regression. So for example, I have an x1 that's just going to be equal to x, the linear part of this, and then x2 is equal to x squared. And so the quadratic part, x3 is equal to x cubed, etc. So I create new variables to account for these polynomial terms. And those new variables are the transformation of that original variable. And so we're not interested in the individual coefficients. In this case, what we're actually interested in is how a specific x value behaves. And so I've plugged in this x naught here, this x0, to basically indicate that we're interested in basically some function of this particular x, and we want to know how it would behave kind of under these circumstances with this polynomial. Or more often, what we're really interested in, rather than how a single x value behaves, is maybe the change between two values. So basically the change between a and b. And so that's going to be like this, where you take the function of b minus the function of a. And so this is basically going to be the linear regression model when x is equal to b minus the linear regression model when the x is equal to a. And so these are going to be individual values, because those will be the predicted values for your y at these given x values. And it's going to be equal to the beta hat 1 times b plus beta hat 2, b squared, beta hat 3, b cubed, beta hat 4, b to the fourth, minus beta hat 1, a, beta hat 2, a squared, beta hat 3, a cubed, beta hat 4, a to the fourth. Now, why don't we have a beta 0 in this model here? It's because when we plug it in, we end up with a beta 0 for this first part, but then we subtracted beta 0 for the second part, so they just cancel out. So there is a beta 0 in this model, but they just cancel out when you're looking at the difference or the change between two values. And so I can rewrite this like this. I think this is a little bit of an easier way to think about it, where instead of writing out this equation kind of where the A's and B's are separated out, I can write it like this, where I'm looking at beta hat 1 times the change between B and A, plus beta hat 2 times the change in those quadratic terms, plus beta hat 3 times the change in the cubed terms, plus beta hat 4 times the change in the terms to the fourth power. So how do you pick A and B? Well, sometimes there's content matter expertise, like you're interested in particular values, particular changes in values. Maybe that's the scientific question at hand. But when you're given no other information, if there's not sort of a different scientific question at hand where there's a specific A and B that are of interest, a sensible choice might be to choose the 25th and the 75th percentiles of X. So for example, coming back to our polynomial regression example, here the 25th percentile of age is just a little bit less than 25. The 75th percentile is a little bit less than 75. And so I can look at a change between being in the 25th percentile to the 75th percentile in population. And so what I want you to do is, using the information below, I want you to go ahead and open an application exercise. So open an RMD file. And using this information here, I want you to write out the equation to predict the change in the population from a change in age from the 25th percentile, which in this case is 24.5, to the 75th percentile, which in this case is 73.5. I'm going to give you 3 minutes to work on that.